let's take this differential equation. So dy by dt plus y equals x of t. Okay. And then you are typically you need to give some initial condition, else you cannot, if you don't know where it starts, you cannot solve for transients at all. Your y of 0, let's say yes, y naught. Simple first order differential equation. First derivative, first order diff. Okay, so I have again couple of questions. First again, put this in English and then we'll go. I'll solve this in math. Okay, I have question 1. What happens if x of t is 0? Happens. Question 2. If x of t step in a suddenly you close a switch, the voltage, now the battery voltage is seen in a RC circuit, for example. If there's a step, let's say a naught u of t, what happens? Okay, Q3, general x of t happens. So what happens? Can you put this into words first? How do you, what happens? And then typically, if x of t is 0, what happens? Fairly easy question, no? First order system, can anyone recognize what is this tau? Let me write this down here. 2 q1. Okay, what you have here is tau dy by dt plus y equals 0, and then you are with y at time t. Initial condition is y naught. Your initial condition. Anyone remember the solution for this? So let's see. Now your dy by dt is minus 1 by tau into y. It's a function of t. This is a function of t. This implies t of t equals this. Again, we know first order system. So some of you, let me put this in English. Let's see if we can recognize that. So rate of change y equals it's proportional to this, proportional to current value of y. Current value of y. Then If you had to guess a solution, what would you guess here? Consider this as quick recall for engineering mathematics. Simplest to first order equation, constant coefficient. The coefficient here is tau 1. What do you guess? Or, based on rate of change of y is proportional to current value of y. See, notice the characteristic equation. This is tau m plus 1 equals 0, m equals minus 1 by tau. So that is your y of t equals some constant a e power mt. It's your solution because you are guessing e power mt as a solution, exponential solution. Derivative is same as the function. Okay, so that gives you a e power minus t by tau. And then you also know that the initial condition shows up y of 0 equals, if you substitute 0, y of 0 is not, that equals a. Take this term is essentially 1. So you just got a a. So your solution y of t value into e power minus t by tau. First order transients. This is first order decay. At least some of your memory got refreshed. You didn't understand this slide. Hey, this is engineering math. This is characteristic equation of this. It's a first order differential equation, constant coefficient. What is a characteristic equation? Wherever your derivative put m, why does that show up? You are guessing e power mt as a solution. So this is the characteristic equation. If this is a characteristic equation, you got your solution is going to be all the sum of the, this is the root of that characteristic equation. And then, so if that is a root, your solution is e power minus mt, right? I substituted m. That is, I suppose you needed I had to refresh your memory, right? Not that is at least from my perspective, it's understandable. Forgot this, right? I suppose that is the case. That is perfectly fine. Let me also write this. This is characteristic equation coming from is e power mt. This gives you the characteristic equation. So how does this look? This is, notice this is a first order system. Okay. And its time constant is tau. If you plot this, it will look like this. Wherever y naught is going to decay. Naught could be here, any other y naught. Where you start, decays. Wherever you start, it could be negative y naught also, but it's going to steady state. So they are all headed to 0. That is point number 1. is t tending to infinity, your y of t tends to y of t notice tends to 0. So that is this is your steady state thing. In this case, this is what we refer to as steady state value. You could also call this equilibrium or steady state value. So any typical first, RC circuit, LR circuit, you take Maxwell model, Kelvin model, anything, MRI, bioinstrumentation, PCT, all of that will, at least starting point is this equation. Tau will change. Tau will be RC for RC circuit, L by R for LR circuit. Each problem will have its time constant, but this is always going to be this equation. This is also what I call the most important problem in non-core subjects, right? The first order transients. Okay, now so that was our differential equation. What happens? That is, this is referred to as the input. In this case, no input. We just answered that. You don't perturb the system at all. The system itself has a natural response. Okay. Again, I'll come to that. This is the case we just studied. This is the no input case. Answer this. Right hand side is 0. You just solve for it. The next question. Input is at least, this is a step function. It's a constant, let's say. How do you deal with this? I'll solve it for you, but at least someone just tell me like what is how to approach this. So in this case, so you just had the difference between this and this is now you had a resistor, capacitor. Okay, and these two are technically connected. You have a charged capacitor, seeing how that is uncharging. There is no input here, voltage. What we are saying in this case is same resistor, capacitor, there is a voltage here, and all of a sudden we close the switch at t equals 0. That is where we get A naught, your voltage, right, suddenly gets applied to the system. General case, you are speaking or something like that, there is a sensor signal. This is any general function of time, x of t. The three scenarios correspond to that. So right now I have a constant battery input. I close the switch at some time at t equals 0. Okay, t equals 0, I close the switch and see what happens here. No input case, just a resistor and capacitor. No external battery. The capacitor is initially charged. How would it discharge in the presence of a capacitor? So closing the switch at t equals 0 mathematically corresponds to u of t. If you look at the net input voltage applied here in the circuit, 0 voltage, at t equals 0, the voltage suddenly becomes V naught. So anyone tell me how to, just again, two words. How do we solve this question? That is, suddenly the switch closes. We want to know this as a function of time. Okay, let me solve this for you. Q 2.2 y by dt plus y is a naught u of t, step input. And your initial condition, your with a of 0, let's say this is y naught. So we use, this is finding. Oh, the question is find y of t, right? So in this case, this is referred to as transient response. The first part we saw frequency response. So as a function of time, how are things going to behave? Because now things are not sinusoidal. This is not a sinusoidal that we are. Input could have been sinusoidal in a general scenario, but right now this is nowhere. It's not sinusoidal. It's a step. In a general scenario, that possibility is there. So this is transient response. What we do is take Laplace transforms. Okay, if I take Laplace transforms on both sides, I get tau into s y of s minus y naught. That is a Laplace transform of dy by dt. Y of s equals. Let me substitute this in a moment. Okay, so your y of s, this gets multiplied by tau s plus 1 equals x of s plus tau y naught. Okay, so your y of s equals x of s by tau s plus 1 plus tau y naught by tau s plus 1. This is due to initial condition. Response due to initial condition. Initially, things are capacitor is charged are non-zero. This is due to input, applied input. Now the two are adding up. That's your total response. Okay, now let's say this is now let's apply our input criteria. The x of s, this happened to be a naught into 1 by s. U of t that transforms to a naught is a constant, u of t transforms to 1 by s, right? So in this case, now your y of s, let me write down the two terms separately. Okay, 1 by s tau s plus 1 and then plus tau y naught by s plus 1. There is also a naught here. What is the Laplace transform of this s square? We do not know, so we have to do some method of partial fractions. Quickly notice, if I write this as a naught is a constant, I want to write this as a by s plus b by tau s plus 1. Okay, then this term remains, so tau y naught by tau s plus 1 How do I get A? I'm going to do this fast. Remove the singularity, tau, let me also have this A naught separately here. This is 1 by S into, right? So remove the singularity, substitute S as 0. I get A naught into 1. I have explained this, method of partial fraction, so I'm not doing the steps, okay? Or I am not explicitly writing down the steps. Do I find B? Remove the singularity, substitute S is minus 1 by tau. So B happens to be minus 1 by tau. So B will be minus tau. So quickly check, this will be tau s plus 1 minus S tau, that will be 1 by S into tau s plus 1. So whatever I have in the bracket will simplify to this term. Okay, you could at least verify that. This tells you y of t. What is the, if you take inverse Laplace transform, what do we get now? Just have 1 over s, and then tau is a constant, tau by tau s plus 1. You could also write this, if you want, let me write this as, you have a naught by s minus a naught by s plus 1 by tau. That is this term. Then you got y naught. Y naught is a constant, s plus 1 by tau. Certain very convenient form where you can easily take inverse Laplace transform. What is the Laplace transform of this? What is the Laplace transform of this? U of t goes to 1 by s, and then e power minus at maps to 1 by s plus a. Now, okay, great. So a e power, yeah, thanks, at least one of you, right? So a naught is a constant. So first term is a naught itself. You can write a u of t if you want to be like happy, right? But this is for t greater than 0. So first term is a naught. Second term is a naught e power minus t by tau. Third term is y naught e power minus t by tau. Notice when we had no input, this is the solution that we got. With step input, we got this additional thing. So this bit, due to till condition, this bit is step input. The term for this is forced response, forced output, forced response. This is goes by the name natural response. That is due to the initial condition. Natural or free response. Now there is a function of time, and then there is a function of there is a constant. Can slightly write that as, so this is a constant plus I naught minus a naught into e power minus t by tau. Notice this term goes to 0 if t is infinity. So this is your y of t. So this is y of t all along. One more way to characterize this. This is a time dependent part. This is a transient response. You look at it, what is changing as a function of time, what is changing as a function of frequency. This is the steady state value, equilibrium or steady state response, steady state value. After a long time, it's going to go to a naught. Okay, initially because of initially there is going to be some transients. if the initial condition that you applied is 0, you just have a exponential saturation. So in fact, in frequency response, you could also this is for a step input, right? Instead of a step input, if I put sinusoidal, what happens? Again, you will be technically able to split it into two, a function of time and just a sinusoidal thing. In frequency response, we just studied this. Okay. So the same function, two ways to look at it. Due to initial condition, due to forcing, or due to input. That is one way to look at it. A changing part, and then there is a steady state part. There is a different way to look at it. In fact, for plotting, the second way is useful. If you plot this, the function is going to be this. Not as equilibrium value. Not as initial value. It's always going to go to A naught. Where you start, it will eventually saturate towards that. Start from here, again that will saturate towards that. Okay, let me draw that blue curve slightly better. Charging of a capacitor. Yeah. The capacitor starts from 0, it will go there. It can also have a initial value that is higher than the equilibrium value. Then it will saturate to this. Equilibrium value could be negative. It will saturate to all negative values. Why not? Right? This is this curve. This is a set of responses that we have. Okay. So note t tends to infinity, e power minus t by tau, t tends to infinity, this tends to 0. So there is no transient response. They all go to that equilibrium value. Steady state or equilibrium. Bottom line, frequency response, what do? We care about input and output, amplitudes and phases. This is typically, initially there is some transients and all that, we don't care about it. Initial first over, there is sudden fall off wicket and all that, fine, but test match, what happens? Right? Or steady state, what happens? That is the question. You can use Fourier transform, frequency dependent transfer function to do that. Also, we had a transfer function. Notice here also technically we had a transfer. If you want to study things as a function of time with the initial condition, to use Laplace transform. There is a transfer function here. Notice this is your transfer function. X of s 1 by 2s plus 1. This is a transfer function. This transfer function, and this is to side input. Notice output is x of s into h of s. So this term, this is your h of s. Again, first order system is the simplest example. Minimum working example, you need to know at least what happens to a step that is given here, and then what happens to a simple sinusoid, what happens to that is also discussed. Okay, so two minimum working examples. And again, every year questions are there from what we saw today. Okay, but if you understood it, you can easily grab those marks. Okay, fine. Let's stop here. We are 10 minutes over time. Let's stop here. And if you again go through the notes, I suppose if you have doubts, it will be clarified.